Hello. Today I would like to show you another movie, and this time specifically about the wind impact on ships' maneuvering motion. And again, I will try to explain the behavior of the ship by the SAMMON planning tool based on fast time simulation. I have planned 3 different small movie clips. The first is for drifting under wind with no propulsion, so poor drifting, maybe by means of the thrusters to work against the weather or to change the drift speed and direction. The second part is ship motion on straight track under wind. So the ship wants to go straight, and we need to know the rudder and the drift angle to avoid the leeway of the ship and to find out the course balance and maybe limits of the steerability if the wind is too strong or the ship speed is too slow. And the third part is then about turning, so wind impact on turning motion and options for increasing the turning capability if maybe the wind is really working against the turning effect of the rudders. Okay, so as I said, we want to demonstrate all these nice things by the SAMMON planning tool, and I will switch now to the fast time simulation. So here we are. This is the SAMMON planning tool interface, and as you already know, here are the handles for setting propulsion, not on this time, but also the bow thruster, stern thruster, and also the external effects from wind. We could also do current, water depth and whatsoever. And here we are with this ship laying idle. And the first we want to demonstrate is what drift speed we can achieve only by means of the thrusters, to afterwards find out to what extent we can manage to work against the wind. Okay, so let's start first with the stern thruster. We are moving the stern thruster to full 100% to the to port side. So what you see immediately that the ship will make this turn, and these are the shapes representing always 60 seconds, 1 minute is one shape, and for the time being we have only displayed 12 shapes. That means for 12 minutes. We could also do it for 24 shapes, because this will be always calculated every second. And if we want to find the balance against the wind, then we use the bow thruster. If we use the bow thruster with 100%, then we see the bow thruster is more stronger than the stern thruster. So the bow will move against it, but we want to achieve a parallel drift. So we have to reduce the bow thruster to 90%, to 80%, to 70%. So what we see here is you will really work in parallel transverse motion, and every shape is 1 second, and the bow thruster is 70%, the stern thruster is 100%. To know what happens on each time at the maneuver, we can move the time slider here down there. For instance, every minute. Then you see that after the first, after the first 10 seconds, the stern thruster is already at 100%. And if we want to, after 10 seconds, then we can use it for 20. So this is after 1 minute. We already have achieved a drifting speed of 0.84 knots. If we go further, so this is after 2 minutes, we are already at 1.39. And if we go further, so this is exactly 600 seconds. That means after 10 minutes we have been here. And the final drifting speed only by means of the thrusters is 1.75. So let's keep that in mind. This is without wind. So the question is now, can we stand also a high wind speed? Then we have to set here down there the wind direction. We will have the wind from north, so 0 degree, and we will set the wind speed to, let's say, 20 knots. And we will see whether or not the ship is able to stand this one. So 20 knots of wind. So we see, okay, the shapes are squeezed together, but the ship is really able to move against the wind with a drift speed of half knot. If we increase the wind speed now by up to 30 knots, so we need again our small tableau. I could do it also in my tiny laptop computer, which goes much faster, but for reasons of the demonstration, I will do it with this tiny panel. So we set it now to 30 knots of wind. And the question will be, can we stand 30 knots of wind? Enter. Then we see, no, we don't. So clearly with 30 knots of wind, we go here with this drifting speed of 1.5 knot. We will drift with the wind with 30 knots of wind. Okay, this should explain that the limit for keeping the ship at station against the wind might be between 20 and 30 knots. If we really try it out here, you will end up about at 25 knots wind. You can stand with this vessel. So the next we want to do is we will switch off the thrusters to see what the ship is doing only with the wind effect. So no thruster against the wind. So what we see here is that the ship is drifting with 2.26 knots, and the drifting is at bow and stern nearly the same magnitude. And the direction of the drifting is, in a way, if you look here, so the course of the ground is 187 at this position, 187. So the ship is slightly going in the stern direction, and the bow, the heading is 94.5 degree. That means the bow falls a little bit downwind, so to say. You might ask, why is that? Why is that that the bow falls a little bit down for this ship? And I should say that this ship is a cruise ship, Aida Blue, and it's a ship with a length of 240 meters, and the 50 meters, the beam is 37.8 knots. And we want to, explain why the ship bow is falling a little bit down and how it comes that the ship achieves such a certain balanced condition and equilibrium. For this, we will dive a little bit into the theory of wind effect on ships, specifically for the effect with no propulsion for the time being. Okay, so here we are to explain the dynamics of ship drift, and we have chosen two examples. First one is the ship like Aida Blue. So the center of the above water area, so the wind area, is a little bit forward of the center of gravity or at the mainframe of the ship. And so it explains that the wind force attacks the ship fore of the center of gravity. of the half ship's length. So this is a red arrow. And if the ship starts drifting, then there is a hydrodynamic force acting underwater in the opposite direction. And if the drift speed is constant, then both of these forces needs to be equal. But what we see here is if the center of the water plane of the wind area is ahead of the half ship's length, then there's a lever between the wind force and the underwater drift force. And the location of the underwater drift force is more to the aft if the ship is trimmed to the stern, for instance. So this is a tendency. And you might understand what happens if we let the ship now move, then this lever will cause that the ship is turning a little bit until it finds an equilibrium. We will show that again in the fast time simulation. But here, in contrast to this ship, we will later show another sample where the center of the wind area is to the stern. And if the ship is trimmed to the bow, then the hydrodynamic force works on the ship ahead of the midship position. So this time the lever or the moment, the turning moment, is in the opposite direction. And for this ship, the ship might go in this direction. So this is the next slide. So again, to say, for this reason, the bow turns out of the wind, it falls downwind, and here the bow turns into the wind. And this is shows the situation after a while when the ship is in a steady state condition, drifting with constant speed. Then you see that the wind force and the hydrodynamic force acts at the same position. So no moment anymore, the forces are equal, so the ship is drifting with constant speed and the bow is a little bit falling down. And the opposite is here for the ship with the center of the wind area to the stern. Then you see that the bow turns into the wind, and again the forces are equal in the magnitude and they're acting at the same position, so there's an equilibrium and balance of forces and moments. So now we want to demonstrate what happens if the thruster comes into the play. Specifically first for this ship, we will keep first this sample. And if you use a bow thruster or stern thruster, then you change the equilibrium and the ship will go to another situation. Okay, here we are back again. So this is the situation when the ship is drifting, still without any thruster. Now we will use first the stern thruster alone. So if the stern thruster is fully working against the wind, like this, then we see the ship cannot be turned by the thruster, the stern thruster alone. But what we see is the heading and the course is changing. So the course is now 203 degree, so about 23 degree out of the downwind direction. And the drift speed we can achieve, or the drift speed decrease we can achieve is 2.10 knots. So we are a little bit slower than the 2.25, 2.4 which we had without the thruster. By the way, I should also mention that these 2.2 or 2.3 knots, this is about 7 to 8% of the wind speed. There's a rule of the thumb that with the drift speed without thrusters is about 8 to about 8% of the wind speed. So for 30 knots, we get 24, 22, 3 or so knots. Okay, this is with stern thruster. What can we achieve with only bow thruster? To 0. This is the next option. So this is a bow thruster to 0, and we the stern thruster, and now we only use the bow thruster. So fully to port side. So what we see is, because the bow thruster it's powerful, it has 30% more power than the stern thruster. So you see that the speed over ground we can achieve here is only 1.86 knots, and the drifting the direction is 156 degree. So this is about 24-25 degrees off of the downwind direction. So by means of these two different options, only stern thruster, only bow thruster, we can change the drifting direction in a range of about between 30 and 50 degree. If you have an obstacle here at the lee shore or whatsoever, which you should avoid, an island or whatsoever, so you can very early can change your drifting direction. The question is that already the maximum change of the drift direction we can achieve? We could use the stern thruster additionally, for instance, to use the stern thruster maybe to starboard. So if I use the stern thruster 30 degrees to starboard, then we can even get a drift direction 145 course over ground here. So this is then 35 degrees, so we have indeed 70 degree of range. We could change the ship drift direction. Another option would be to investigate, okay, if we can manage to bring the bow into the wind, would that reduce the drift speed? Because then less area, less windage is exposed to the weather. With this, we could achieve this. Maybe we go to 50% of the stern thruster. So now we see that we can manage to bring the bow into the wind and to have the full drifting speed. We will add some other maneuvering points. So if I go back a little bit until this position and I set a maneuvering point like this here, and then I switch off the thruster at the stern side, and I will adjust the bow thruster in a way that we can really keep the bow into the wind. So this is with 20% only, so with between 16, 20, okay, this is no thruster. Okay, so we can use the time slider to move the ship a little bit downwind, so like here. And there's a new maneuvering point where we will set the bow thruster to the other side to stabilize the vessel, so we can do that several times to find out the balance that we exactly will find the situation where the ship is drifting with the bow in the wind. So this is a little bit playing around with the tool, but it's much more faster than to try it out in the ship handling simulator, you know. So if we move it further down to here, then we see the final drifting speed is then less than 2 knots. So at least it is less drifting speed than in the drifting abeam. But if you manage to get the bow into the wind, then the wind area is less, but the ship is also drifting faster because now it's going astern. We could also use it to turn the stern into the wind and go ahead with the vessel, but this is faster than this one. So this could be a chance to reduce the drifting speed to keep the bow into the wind. Okay, these are the options you have using only the thruster. If your propulsion is out of order and you only have the chance to maybe control the vessel by means of the thrusters, then you have several options we have already shown.